On the Cusp of Understanding. Presented by Science at NASA. Constantly shielding us from the sun's high-energy particles is the Earth's magnetic field. Many imagine this field as a circle slightly larger than our planet, but it's actually shaped like this. And near our north and south poles, there is a cusp, a point where two branches of a curve meet. It's here that the magnetic bubble that surrounds us dips inward, creating a funnel of magnetic lines that touch down to Earth. This funnel allows the sun's high-energy particles to race toward our planet and deposit themselves in our ionosphere, 80 to 800 kilometers above Earth. We can even see the result. They create beautiful aurora, similar to the spectacular displays at night, but on the day side of Earth, and only visible to the naked eye during the long polar night. Now, scientists who want to learn more about effects of these particles are embarking on a special initiative that is taking place from December 2018 to January 2020. In a coordinated effort between multiple countries to understand the physics of the polar cusp, scientists from NASA and the U.S., as well as from Japan, Norway, Canada, and Great Britain, have launched the Grand Challenge Initiative, Cusp, a series of sounding rocket missions that will provide the data needed to conduct 9 unprecedented studies of near-Earth space at the polar regions. This series will help scientists glean answers to a number of questions about the cusp. Why is our atmosphere leaking out into space from the cusp? How and why do the turbulent hot patches of dense plasma that exist inside the aurora region disrupt global communications? What sustains strong updrafts of atmospheric gas in this region that can cause enhanced drag on our satellites as they orbit? Doug Rowland, a space scientist at NASA's Goddard Space Flight Center, explains, "The cusp is a great natural laboratory to understand how Earth's atmosphere responds to direct energy input from the solar wind. This kind of science can be done nowhere else on Earth." 12 sounding rockets conducting the 9 missions will launch from 2 sites in Norway, Andøya Space Center and Svalbard Rocket Range. In some cases, launches will be conducted at nearly the same time from Andøya and Svalbard, providing simultaneous observations at different altitudes and latitudes. Why use rockets instead of satellites or weather balloons? Doug Rowland explains, "Rockets are ideal for taking the measurements we need. These rockets will be packed with monitoring instruments to capture information as they move upward in an arc and on the way down too. They can gather up to 15 consecutive minutes of direct measurements from a specific region of space, and you can launch them precisely. You want your rockets to fly right through the auroras just as they're going off. Satellites cover a lot of area, but at high speeds, they don't spend as much time making observations of any one location. Balloons can't be launched high enough, and their location can't be controlled as precisely as rockets." The new data gleaned from the Grand Challenge Initiative, Cusp, will help scientists make better space weather forecasts and give us a better understanding of the particles responsible for one of the most breathtaking sights on our planet. Take the initiative to learn more by visiting science.nasa.gov.